ExactFlat for SOLIDWORKS. In this example, we're going to take a standard office chair and prepare this chair for flattening and create flat patterns from it. This chair was modeled from scratch in SOLIDWORKS using both solid and surface bodies. And the first thing we're going to do is we're going to create pieces. These are pattern pieces. We're going to start our timer here. And to create the pattern pieces, we simply select the bodies, whether they be solid bodies or surface bodies, and then click Create Piece. And you can see when the piece is selected, it becomes highlighted. And after the piece is created, it becomes transparent and locked for editing. And this should only take a couple of minutes. The Piece Creator is a tool that we built that will save time in going from a faceted CAD model to a model in which pattern pieces are analogous to those which are going to be manufactured. So this back panel is actually going to be one sheet of fabric, so we'll just join these pieces together. And what the algorithm does is it just knits and welds these pieces together. And we're just coming up to the end. That is all of our pieces. We're just going to reorient our piece here. Click OK. And the algorithm is now going to knit and sew the pieces together. And this should just take a second. The next step in our workflow, once this is complete, is to actually lay our pieces out. And there you have it. There the pieces are created. So now we're going to click on Convert to ExactFlat. What we're going to do now, or what the program is doing now, is it's indexing adjacent pattern pieces and creating a UV mapping along each adjacent edge so that things like notches and seam allowances can be lined up automatically in subsequent steps. But for now, first step is we're just going to assign a material here. So we're just going to assign the same material to all these pieces just for the sake of brevity and demonstration. And there we have it. Pieces are assigned. Together with those pieces, we will also assign engineering characteristics such as Young's modulus and Poisson ratio in addition to others. And before we get into our flattening environment, we're going to arrange these pieces in a manner which is going to be more or less representative of how the pieces are going to be sewn together. We do this just so that it's a visual and intuitive check for designers so that they can see how pieces go together. It's going to save some time when we get to subsequent pattern engineering. It's not a necessary step at this stage, but for us it's a best practice that we've adopted. And we're just using our Move tool here, and you can see that we can either move the pieces around or click on an edge and align them up with a certain offset from the primary edge. And that should be sufficient for starting the flattening process. So we start the flattening process by clicking on the flattener environment, and you can see we have the 3D model on the left and the 2D pattern pieces on the right. The initial model is based on a fracture, which is essentially taking the polygons in the mesh and breaking them up and laying them flat and then sewing up any gaps. So it's a non-developable surface. You're going to have some pretty significant distortions, as you can see here. What we're doing right now is creating an analysis mesh. The analysis mesh will be optimized for the flattening algorithms. It will decrease solve time and increase pattern accuracy. It just takes a couple minutes to mesh all these pieces together, as you can see. And when they are finally all meshed together, not meshed together, pardon me, when they are finally having been completed, the meshing process, we can select them all and then start the optimization process. You can see the stress and strain and sag indications based on the colors change with a different mesh as well. The analysis mesh better represents the geometry. And now here we are well into our optimization process. You can see what's happening now is that the vertices of the polygons are able to walk and reorient themselves in such a way that strain or stress on the pattern piece as well as sag are minimized. And you can conceive this by thinking in terms of the energy in a piece of fabric or a piece of cloth. When you take a piece of cloth and you pull on it, it will stretch, and there's going to be a tendency for that to return to its original form. The degree to which it does this will be based on the type of fabric and its engineering characteristics, its Young modulus, for example. However, when the fabric is stretched, what we conceive as far as our algorithms are concerned is that the cloth has some energy in it. and it seeks to minimize the average energy density across the piece. You can see now it's finished. We're going to rebuild our pieces. This will redraw the perimeters in a way that is going to take into account the optimization that just happened. And this should take a couple seconds just for it to optimize. And there you have it. There are your pattern pieces that should correspond to the pattern pieces that would be produced in a manual pattern making process, but in this case, in a couple of minutes, 5 minutes or so. If you want to know more, visit our website or give us a call. Thank you very much.